In general, you have to be able to do the multiplication by yourself without using a computer calculator. But in the exam and in the homework, you basically have your calculator and your computer in front of yourself. But it's important to know how to do the multiplication, because later if you want to prove something or verify something, we need to know how the multiplication is happening. In other words, we need to know this formula. So what is BA? What is the result of B multiplied by A? It's not possible. It is not possible. If we have that result possible, if we had that multiplication possible, in other words, if this was an S-square matrix, this was also an S-square matrix, can we say that A multiplied by B will be equal to the B multiplied by A?
No.
No. In general, even if the multiplication is possible, A multiplied by B is not necessarily B multiplied by A. We can come with hundreds, thousands of examples which the result is the same, but it is not enough in order to generalize it. Now we want to talk about another important terms that we are using it in vector analysis and in matrices, which is the norm of vector. So we'll start by talking about the vector. We see the properties of the norm of the vector. Again, this is something that you might know, but it's very important, because later we want to talk about the norm of a matrix. And this is very important in, let's say, image processing, because we can use the norm in order to represent some properties of the image. So we start by talking about Euclidean norm of a vector, and let's say that U belongs to Rn, then Euclidean norm of U, this is the notes that we use, is S square root of U1 square plus till term UN square, which is the inner product of U by itself to power 1 over 2. What does a vector norm represent? Do you know? The Euclidean norm of a vector, known as vector norm, shows the length of a vector. So it basically shows the length of a vector. And it has some very unique and important properties. Which kind of also inherited from the fact that it is an inner product. What can we say about if U is not a zero vector? What can we say about the norm of U? It is definitely positive. And if U is a zero vector, the norm of U is 0. Now, what can we say about if you are multiplying a vector with a constant k, which is a real number?
K times.
It will be absolute of k multiplied by norm of U, because norm is always positive. K can be a negative number, we know that here we are handling negativeness. Everything is positive. Everything is positive. What can we say about if we are adding to vector? What can we say about the norm of the addition? It is always less than equal to addition of the norms. Do you know what is the name of this formula? It's called triangle inequality. You know, the addition of, for a triangle, the addition of two of the lengths is always greater or equal than the third one. This is what this formula says. And there is also one more inequality, which these three properties, maybe you knew it from undergrad, but this one is kind of new, which is known as Cauchy-Schwarz inequality. And it says that if u and v are vector, the norm of inner product of u and v is less than equal to norm of u multiplied by norm of v. Norms are very important, and we have different form of norms. We will see that the term Euclidean norm is just another name for norm 2 of a vector. So we understand that we can have norm 1, we can have norm p, we can have norm infinity of a vector, and norm 2 is just one of the norms. But this is a very well-known norm because it represents the lengths of the vector, so we have a special name, Euclidean norm. And in practice, in many of the sciences, when we are saying the norm of a matrix, the norm of a vector, we mean norm 2, we mean Euclidean norm. In this course, you will learn all different type of norms, what they represent, and we will see how they can be used in computer science basic, each of them. Okay? So this is just because it is a revision, and in undergrad you might have seen this second norm or Euclidean norm by just defining it the norm of the vector. But we understand that this is actually norm 2, and we have different type of norms, and we will discuss about those type of norms. Now, getting back again to the Euclidean, inner product, and geometrically, one can say that if we have the inner product of u and v, actually this inner product is equal to, because this is a scalar, we know this is a scalar, it is the norm 2, the Euclidean norm of u multiplied by the Euclidean norm of v multiplied by cosine of the angle between them. Right? Again, this is a very, very well known. So, why do we need to know about this geometrical representation? Because we want to define two very important terms. If U and V are perpendicular, in other words, what is theta? 90. Or we write as pi over 2. Then U and V. What is U and V? The inner product of U and V? 0. And we call them, there is a special name for these two. Do you know what they call? Orthogonal. So, we say that if I tell you that, oh, we have a vector A and B and they are orthogonal, you understand that it means they are perpendicular. We call it perpendicular and we can show the perpendicular in the 2D, 3D very easily. But we can see that they can have n dimension. In order for us to understand, it means that the inner product is 0. And if U and V, if the norm 2 of U and norm 2 of V is equal to 1, what does it mean? Norm is equal to 1, it means they are unit vector. The length is 1. And if they are orthogonal, we call them. Now, if they are unit and orthogonal, we call them orthonormal. We call them orthonormal. Now, these two terms, we will use them infinity many times in this course, and we are swapping between orthogonal and orthonormal quite a lot. And this property that they are perpendicular, and this property that not only they are perpendicular, but they have the unit length, are very useful for many of the proofs, because in the theorems we have that if we have vector u, v, w, x and y to be orthonormal, then we have some properties, and when we want to prove the properties, we are benefiting from ortho property, which means they are perpendicular, and normality, which means that they are unit. Okay? Now, one question. Geometrically, as we have talked of geometry, let's ask this one. What does norm of the column vector x belonging to Rn show? I'm calculating the norm of x. You remember how to calculate the norm of the x? It's x1 squared plus xn squared all under the square root. So what does it geometrically, what does it show?
Length.
Length is the definition, but what geometrically what does it show? So I mean, length is not a geometric term. There is another term, another word we use it. It's the distance between the origin and this n-dimensional point, antipole that we have, right? So if it is two-dimensional, so it has only x and y value, let's say. So what does the inner product, what does the norm show? It shows what is the distance between the origin and these values. So we can say that distance between the origin and the n-tuple in n-dimensional space. So let's ask an example, and I want you to answer it and solve it. So it's not numerical, so you are practicing. It's good in the early morning, you are practicing some multiplication. You will get ready for the rest of the day. And the example is this. Given that we have vector 2, 0, minus 1. So we have the column vector x1, the column vector x2, and the column vector x3. So if I use the term vector, we mean column vector. Check the orthogonality and orthonormality of x1, x2, and x3. So we have three column vectors. Remember, when I am typing the questions, when we are providing you a question to solve, or when I'm writing on the board, writing in a column form, column vector is taking lots of space. So for me, it's easier to write it in the row form as a row vector, but we know that it should be a column vector. That's why that I'm putting this transpose. So it means that actually x1 is a column vector which is 2, 0, minus 1. Or x2 is a column vector which is 0, minus 1, 0, and so on. Okay? So when I say it's a column vector and I write it in the row form, I put the transpose in order to be correct, because simply it takes less space when I'm writing it. So one of the things that we can quickly answer is, we have to check two things, orthonormality and orthogonality. Which one of these two we can actually answer very quickly with one quick look?
Orthonormality.
Orthonormality, we can see it. Why? Because orthonormality tells us the length, the norm, the second norm should be 1. And the second norm of a vector means that a square root of u1 squared plus u2 squared plus u3 squared, right? And easily you can see that if you are squaring, let's say these ones, and add them, it will not be 1, right? It will be 4 plus 16, 20. So it's a square root of 20. So definitely we know that it is not orthonormal. Why it is not orthonormal? Because orthonormal has two conditions. It has to be orthogonal and it has to be unity. It has to be, the norm should be 1. And because this fails, it is not orthonormal. But for the orthogonality, we don't care if it is normal or not. What you have to do, you have to check the inner products, which I want you to check. And I think it should be orthonormal. I don't have the answer, but it should be like orthogonal, but it's not orthonormal. Please. Did you check? No. Okay. Easily again you can see, because we are multiplying the correspondence to each other. x1 multiplied by x2, the 0 confirm. x2 multiplied by x3, 0. Confirm. Now we have to check x1 and x3. This is 4, this is minus 4, so it is 0, so definitely it is orthogonal. But it's not orthonormal because one of them not to be unit is enough for me. I don't need to check for the rest. So we have discussed about the norm. By norm we mean the second norm. We will discuss about the other norms in this course later. We talk about the norm, the second norm of a vector. Let's see how we are defining the second norm of a matrix. Because the second norm of a vector, we said it gives us the length of the vector. Right? It gives us the length of the vector. So what about the matrix? I mean, the matrix, we cannot talk about the length of the matrix. So what we want to do is that we want to revise what was the matrix norm. And I put the 2 in parentheses. Right now, every norm that we talk is norm 2, but we know that we will talk about the other norms much later. So, it shows the maximum magnification of a matrix. It is the maximum eigenvalue of the matrix. In some books, it is referred to the gain of a matrix. In other words, gain of a norm of a matrix is maximizing the gain of any vector x which is not 0 over a, which means maximizing the norm of ax over the norm of x if x is not 0. And this is a definition that we will see how we can use it in a few minutes through some examples. But let's talk a little bit about what we mean by the norm of a matrix. It shows the maximum eigenvalue of the matrix. How we use it in computer science, let's say in pattern recognition, is this. We have sets of patterns, we have sets of elements, and we want to find in which direction through this pattern I have to draw a vector, I have to draw an axis, which if I am projecting everything on that axis, I can have the maximum variation between my pattern. In other words, how I can come up with a new dimension, which if I am projecting all my data in that one, I will have the maximum discrimination. And then, if I am calculating the second norm of this set, which is a matrix, it will give me the maximum eigenvalue, which tells me what is the it gives me the direction of this axis, which gives me the biggest variation. This is how a method called principal component analysis works, right? Now, or we are defining it by having this formula, which is the definition of the gain. Now, gain of a matrix is defined that if I am multiplying any given vector x by this matrix, I will get the maximum number, right? So, for any matrix x, this should be maximized. So, in order to calculate and find the norm of a matrix, I will go back to this formula and we will see how we can use it in order to calculate a few of famous norms. But before that, let's go over a few properties. Because we need to have the properties plus this formula, then we can easily calculate the norm of a matrix. Given that A belongs to Cn by n, which means that A is a square matrix, norm of A and norm of A conjugate are equal to each other, and apparently it is equal to the A norm of A transpose. So if I know one of these norms, I know the other ones because they are the same. If I have the addition of two vectors, the norm of the addition of the two vectors, it is always less than equal to the norm of A plus norm of B. In other words, I can always find what is the upper limit of this norm, because sometimes it's important for me to know that if I'm adding two matrices, the norm, which tells me what is the magnification value, what is the gain, is limited. It's not infinity, right? It's important for us in order to discuss about the stability of, let's say, a control system. Similarly, A multiplied by B, the norm of A multiplied by B, if the multiplication is valid, is the norm of A is less than or equal than norm of A multiplied by norm of B, and norm of A multiplied by x is less than or equal to norm of A multiplied by norm of x. Similar to the vector, we can multiply a constant k by our vector, by a matrix, which will be the absolute value of, or the magnitude of k multiplied by norm of A. What if k is a complex number? We know that this means the magnitude of the complex numbers. And if it is a real number, we mean the positive value. And if for a matrix I come to the conclusion that the norm of the matrix is 0, what does it mean? It means A is 0. It means A is 0. And we start, I keep this formula, and we'll start to show the last one first. So if A is equal to 0, then norm of A, which is maximizing over x, which is not 0, of norm of Ax over norm of x is equal to, because A is 0, this one is 0, this is divided by norm of x, which is 0. Okay? Two more examples before I let you go. If A is equal to I, Can you tell me that what is the norm of, do you know what is I?
Yeah. Identity.
Identity matrix. It's identity matrix. The elements of main diagonal is 1, everything else is 0. If A is equal to I, what is the norm? Norm of A is the maximum over x of I multiplied by x over x, which is norm of x over x, which is 1. Which is 1. Of course, x is not equal to 0. If A is equal to a diagonal matrix alpha 1 tell me what is the norm?
Maximum of alpha.
Sorry?
The maximum.
The maximum of alpha.
Oh,
Maximum of absolute value of alpha.
yeah.
You can prove it. I mean, I will substitute and I will come to one point at which I will let you to think about it. This is equal to the maximum of x is not equal to 0 of ax over x, right? Which is maximum, and this one will be a square root of alpha 1 square x1 square plus alpha n square xn square. And this is equal to maximum of alpha 1. We have to check which of the alphas is the maximum, then it will be that value. The result will be that value. What is the norm of x? You can also write this one. It is x1 square So the question is that how from here you can get to this point.
So first of all, it's like this value of bottom is larger than the smallest, smaller than the largest. Like, let's say alpha 1 is the smallest, so it's
Yeah, true, absolutely true. What we can do is that, let's say alpha r is the maximum over all of these, right? Right? So what we do is alpha 1 is square, x1 is square, this is definitely less than equal to alpha r square, x1 square plus alpha r square, xn square, because all the alphas are less than equal to this alpha r. So if I replace everything with a big number, the total result is less than equal, right? So this is, what is this one? This is equal to alpha r s square multiplied by x1 square plus xn square, which is, if I replace it in there, which is alpha s square divided by this norm. Now, we understand that this term and this term will cancel each other, and we have absolute of alpha 1, alpha r. What is alpha r? Which is maximum of alpha I, the absolute value of alpha I from 1 to n. Right? Now, the next thing that we will discuss about it in the next session, and again is kind of a revision still, is the determinant of a matrix. We remember what is the determinant of the matrix. We defined the determinant of a matrix for the S-square matrix. And it was very important in order to find the inverse of a matrix. In this course, we will learn how we can find the inverse of a matrix if the determinant doesn't exist. If the matrix is not a square matrix. We will talk about all of those terms, but still, let's revise everything. Do you have any question? If you have no question, this is the end of the lecture for today. Let me stop.